Maxima and minima problems are a really big thing in maths, sometimes called optimization methods, because you want to come up with optimized solutions. Optimal control theory, all these sorts of things are branches of mathematics that basically use calculus to solve maximum, minimum problems. Okay? To give you an idea of how far it goes, when I was at uni, one of the subjects, optimal control theory, and one of the projects we worked on was a toilet, and we had to try and maximise the amount of waste that it got rid of, but minimise the amount of water it used to make it a very efficient system. Yes, you come up, create functions for that, and then once you've got the function, you can use the graph. And you work out, well, where's that maximum point? Where's that minimum point? How can we solve the problem? The advantage, of course, of using it with a function is I don't actually now have to physically draw the graph, because all I'm really interested in is the actual point itself. And once I've got the point, well, the y value will tell me the maximum or the minimum that I'm looking for, and the x would be the input to get that value. So I no longer need to draw the graph itself. And that's what we try to do with these maximum and minimum problems. We try and reduce it down. So we're going to have some sort of word problem, some practical problem that we need to solve. We're turning pure mathematics into applied mathematics. That problem, we now want to pull that practical problem and bring it back to pure mathematics. We want to bring it back to a set of equations, something we can work with. The ones that we're going to look at, there'll usually be two equations, because we're working in a two-dimensional number system. See, at university, of course, we don't worry about two dimensions. We can keep going for many, many dimensions, and you can have a whole heap of series of equations. The theory is still the same. One of those equations you're looking for is, well, what is it? What is this thing we're interested in maximising or minimising? What is the solution I'm trying to find? And B then would be, well, what information do I know so I can apply the problem? There's some piece of information they've given us. That pretty much covers most of these sort of problems. And once we've done that, well, then we rewrite the equation we're trying to maximise or minimise with only one variable. So we can turn it into a function we can play with. And we do that by substituting in that known information. Then we go and use our calculus and we go and solve the problem. Let's find that maximum point, that minimum point, what solves our problem. I say practical problems, sometimes practical is used very loosely. Mind you, I'm sure you've had this situation yourself. We have a rope, it's 36 metres long. Now we're going to cut this rope into two pieces, and then what we're going to do is we're going to create two quadrilaterals. Perhaps we're going to put it on the ground and try and close ants in them or something, I don't know, whatever we're going to do with them. But one of those is going to be a square, and the other is going to be a rectangle, so two quadrilaterals. We want to find the length of the square so that the area that we capture is going to be maximised. We can put as many ants inside these little, what would they be, pens, I suppose, little pens that we can. Oh, there is another condition there. One side has to be the same in length as the square. It's possible it has to fit into a narrow strip or something like that. So we know one side got to be that length. Now I like to visualise what's happening. So I would end up with a picture like this. I've put down my two pens where I'm going to put these ants. One's a square, one's a rectangle, but we can see one side's the same because it's got to fit in this area. Well, I'll just call the side length S for square. That means my rectangle will be S, and I may as well call the other length R for rectangle. One equation we're going to come up with is what we're trying to maximise or minimise in this case. It's the sum of the areas. Well, some of the areas of these two shapes would be S squared plus RS. I need another equation, some piece of information that they've given me, something concrete that I know. And the other thing I really know is that the rope is 36 metres in length. Well, basically that's going to be the perimeter of these two shapes, because that's the rope I'm using. So I know then that 6s plus 2r is 36. What this now means is my equation over here that I created, what I'm trying to maximise or minimise, initially it's got three variables. I want to bring it back to two because I want to create a two-dimensional problem. I can do that via the second one, because I can make either r or s the subject, it doesn't matter which one, substitute it in here, and then I'll only have two pronumerals, and I can play with the calculus. Which one do I choose? Well, I choose the one that's going to make it easiest for myself, and that's going to be to get rid of the r. because there's only one spot there. For the S, I could do the S, but then I'd have to square and all that sort of stuff. So let's make R the subject. I get R is 18 minus 3S. Substitute it back in, play around with it, and there we go. I've got a quadratic. Now here's the interesting thing. That turned out to be a quadratic, which actually gives us two ways now to solve this problem. Because it's a quadratic function, we also know things about quadratics. If I'm trying to maximize the area, well, where's the maximum of a quadratic? Well, it's at the vertex. So I could find the vertex of this. But that would be a silly example for what we're looking at. I'm going to use calculus to do it. So let's use the calculus. So there's my function I'm playing with. I now need the tool. It'll be dA ds. How does the area change as the side length changes? So if I was to draw the graph, I'd have a picture and it would have, well, if I made the side length this, I could read off the graph and go, well, that'll be the area you get, and so on and so on. I'm looking for the value that will give me that maximum area. Second derivative will come in handy as well there. It's now back to an applied maths problem. We're basically saying, what is the maximum of this function? Well, I know stationary points will occur when that first derivative is equal to 0. Solving that, S is 9 on 2. Now I need to confirm that this does indeed give us the maximum. Sub into the second derivative, I've got a negative value. It's concave down. So yep, concave down. There you go, we have a solution to our problem. Notice they did not ask what the area was. The question simply said, what is the length of the square? Well, I've got that. The side length of the square, and because I'm solving a practical problem, I don't write 9 on 2. I mean, I could. But if you were to say to someone, how long is this? You wouldn't say, oh, look, it's 9 on 2 metres long. You'd say, oh, it's 4.5 metres long. No, I answer it like normal language. So square is 4.5 metres. That's when the area will be a maximum. Now, have a look at that and go back to the original problem. If the side length is 9 on 2, what does that tell us about the other side of the rectangle? Now, where are we? Let's go back. There's our formula. R is 18 minus 3S. Well, the length of the rectangle, if you were to sub it in, also turns out to be 9 on 2. So actually, that rectangle, if I want maximum area, it's when they're both squares. That will give us the maximum area. And in fact, you will find that, unless there are other conditions in play, the perfect shape will always give you the maximum solution, if you can get it to a perfect shape. So if we're talking about ovals, then the circle would be the best rather than an ellipse. Talking about quadrilaterals, then a square would be our best solution. So the optimal solution generally tends to be the perfect shape, if we can get it. The other consideration, which I don't have to do here because we've proven it is a maximum, is if there is a restriction on the domain, which there could be, because remember what S is representing. S is representing the length of the square, but of course it can't be bigger than 36 because that's the length of the rope. Now of course, if it was 36, the area would be 0. It's a silly answer. But there might be ones where actually the endpoints of the domain might give you a bigger answer than that turning point. So sometimes you need to just check the endpoints of the domain to see, actually, does that give me an answer that's bigger than the one I've got? So just be wary of that. It doesn't happen a lot in the ones we see, but it might. Okay, let's do another one. We're going to make a bucket. So we have an open bucket, of course, otherwise we couldn't put anything in it. It would be silly to have a bucket that was there. And we want to hold as much liquid in it as possible. We want to create this bucket. Now, conveniently for the maths, the surface area happens to be exactly 12 pi. Amazing. How on earth they got an exact value out of an irrational number? Who knows? That's the amount of material we have. 12 pi units squared. We want to find the height, the radius, and the volume of this bucket. We are of course looking at very, very simplified problems. The reality of a problem like this is we would need a lot more information, because if you're going to physically make a bucket out of a piece of material, there will be wastage. It's pretty hard to use every piece of material that you've got. This problem assumes that we can magically use every piece of material that we've got. Now, in reality, when we would do this in, say, optimal control theory, we'd have another equation for the wastage, what we don't use, and we'd have to factor that in as well. And obviously that's something we would want to minimize. But our problem we don't have to worry about that. We're going to use every piece of metal, plastic, whatever it is we're making this bucket out of. There's a picture of my bucket. It's a lovely cylinder. It's not the one we traditionally see that's tapered, which of course would have a different volume again. We know the radius and the height, that's the things we're trying to find. Well, there's the formula. We're trying to maximise the volume. Pi r squared h is the volume of a cylinder. Information we know. Surface area. Surface area of a cylinder, which is, of course,
2 pi r.
Say it again?
Pi r squared plus 2 pi r h in this open bucket.
Very good. Yeah. For this problem, it'll be pi r squared plus 2 pi r h, not 2 pi r squared, because it's an open bucket. So we're not going to make a circle to sit on top. We're only going to have one circle on the base. So for ours, it's going to be pi r squared plus 2 pi r h. And that will be 12 pi, and you can see why conveniently it was a multiple pi, because now all the pi's will cancel and makes life very easy for us. Let's make h the subject. That's going to be a heck of a lot easier than making r the subject in this one. H the subject, and we get 12 minus r squared over 2r. Sub it back in. Oh, and by the way, in your solution, you don't have to write make h the subject and substitute back out. This is just me pointing out this is what I'm doing. Okay. I mean, you can put it there if you want. Volume will now be pi r squared times that expression. Let's expand that out. There it is, 6 pi r minus half pi r cubed. If we were to go and draw this, we'd have a cubic. And so a cubic traditionally goes a maximum point and a minimum point. It'll go up and down. Well, we're interested in finding that maximum point. Where is it? Let's find our derivatives. We get 6 pi minus 3 on 2 pi r squared for the first derivative. Second derivative minus 3 pi r. Okay, we know the stationary points will occur when the VDR is equal to 0. Go and solve that. We get two possibilities for r, plus or minus 2. One will be the maximum, one will be the minimum. We need to test. I don't need to test both, because remember, we've turned this into a pure maths problem. It was an applied maths problem. In the real world, you're not going to have a radius of -2 in the real world. So it would be silly to test that one. Let's test r equals +2. And when we substitute in, yep, it's as we expected, it is a negative number. Therefore, it's concave down. So I now know that when r equals 2, the volume is a maximum. But in this one, they did ask for more information. Not only did they want the radius, they wanted the height as well, and the volume. Well, let's substitute back into all the things we have. We have a formula for h in terms of r. It turns out to be 2 again. So there's that idea of perfection. In this case, we're saying, well, for this cylinder, the perfect solution, the best solution, is going to be when the radius and the height are the same thing. So it's a strange bucket when you think about it. It's not what we'd be expecting to see. It's actually going to be quite a shallow, flat bucket rather than a tall one. Subbing to the volume, we get 8 pi. And then we answer the question. Because remember, the question was not find h. We introduced h into the problem. The question was, what is the radius, what is the height? So you tell them, oh, well, the maximum volume is 8 pi units cubed, and this will happen when the radius and the height are both 2 units, when they're the same thing. So 4h and 4i, some of our optimization or maximum and minimum problems to play with.